Hi all, welcome to this session on causality in machine learning as a part of Frontiers in Machine Learning. I am Amit Sharma from Microsoft Research and your host. Now, of course, I presume you would all agree that distinguishing correlation from causation is important. And even at Microsoft, for example, when we are deciding which product feature to ship, or when we're making business decisions about marketing, causality is important. But in recent years, what we're also finding is that causality is important for building predictive machine learning models as well. So especially if you're interested in out-of-domain generalization, having your models not brittle, you need causal reasoning to make them robust. And in fact, there are interesting results even about adversarial robustness and privacy, where causality may play a role. And so this is really an interesting time at the intersection of causality and machine learning. And we now have a group at Microsoft as well that is looking at these connections. I'll post a link in the chat. But for now, today I thought we can ask this question: what are the big ideas that will drive further this conversation between causality and ML? And I'm glad that today we have three really exciting talks. Our first talk is from Susan Athey. She's an economics of technology professor from Stanford, and she'll talk about the challenges and solutions for decision-making under high-dimensional data and how generative modeling can help. In fact, when I first started in causality, Susan's work was one of the first I saw that was making connections between causality and machine learning. So I'm really looking forward to her talk. Next, we'll have Elias Barrenbaum, who will be talking about the three kinds of questions we typically want to ask about data and how two of them turn out to be causal and they're much harder. And he'll also talk about an interesting emerging new field, causal reinforcement learning. And then finally, we'll have Cheng Zhang from Microsoft Research Cambridge. She'll essentially give us a recipe for how to build models, neural networks that are robust to adversarial attacks. And of course, as by now you have guessed in this session, she'll be using causal reasoning. At the end, we'll have time, about 20 minutes for open discussion. So all the speakers will be live for your questions. Before we start, let me tell you one quick secret. All these talks are pre-recorded. So if you have any questions during the talk, feel free to just ask those questions on the hub chat itself. And our speakers are available to engage with you on the chat, even while the talk is going on. All right, with that, I would like to hand it over to Susan.
Thanks so much for having me here today in this really interesting session on machine learning and causal inference. Today, I'm going to talk about the application of machine learning to the problem of consumer choice. And I'm going to talk about some results from a couple of papers I've been working on that analyze how firms can use machine learning to do counterfactual inference for questions like, how should I change prices or how should I target coupons? And I'll also talk a little bit about the value of different types of data for solving that problem. Doing counterfactual inference is substantially harder than prediction. And indeed, there can be many data situations where it's actually impossible to estimate counterfactual quantities. It's essential to have the availability of experimental or quasi-experimental variation in the data to separate correlation from causal effects. That is, we need to see whatever treatment it is we're studying, that needs to vary for reasons that are unrelated to other unobservables in the model. We need the treatment assignment to be as good as random after adjusting for other observables. We also need to customize machine learning optimization for estimating causal effects and counterfactuals of interest instead of for prediction. And indeed, model selection and regularization need to be quite different if the goal is to get valid causal estimates. And that's been a focus of a lot of research, including a lot of research that I've done. A second big problem in estimating causal effects is statistical power. So in general, historical observational data may not be informative about causal effects. If we're trying to understand what's the impact of changing prices, if prices always change in the past in response to demand shocks, then we're not going to be able to learn what would happen if I changed the price at a time when there wasn't a demand shock. I just won't have data about that from the past. So I'm going to need to run an experiment, or I'm going to need to focus on just a few price changes or use statistical techniques that focus my estimation on a small part of the variation in the data. Any of those things is going to lead to a situation where I don't have as much statistical power as I would like. Another problem is that effect sizes are often small. Firms are usually already optimizing pretty well, so it would be surprising if making changes leads to large effects. And the most obvious ideas for improving the world have often already been implemented. Now, that's not always true, but it's common. And finally, personalization is hard. If I want to get exactly the right treatment for you, I need to observe lots of other people just like you, and I need to observe them with different values of the treatment variable that I'm interested in. And again, that's very difficult, and often it's not possible to get the best personalized effect for someone in a small data set. Instead, I'm averaging over people who are really quite different than the person of interest. So for all of these reasons, we need to be quite cautious in estimating causal effects, and we need to consider carefully what environments enable that estimation and give us enough statistical power to draw conclusions. Now I want to introduce a model that's commonly used in economics and marketing to study consumer choice. This model was introduced by Dan McFadden in the early 1970s, and he won the Nobel Prize for this work. And the main crux of McFadden's work was to establish a connection between utility maximization, a theoretical model of economic behavior, and a statistical model, the multinomial logit. And this modeling setup was explicitly designed for counterfactual inference. And the problem that he was starting to solve was what would happen if we expand BART, which is the public transportation in the Bay Area. What if I expand BART? How will people change their transportation choices when they have access to this new alternative? So the basic model is just that an individual's utility depends on their mean utility, which varies by the user, the item, and time, and an idiosyncratic shock. In general, we're going to have a more specific functional form model for the mean utility, and that's going to allow us to learn from seeing the same consumer over time, and also to extrapolate from one consumer to the other. We're going to assume that the consumer maximizes utility among items in a category by just making this choice. So they're going to choose the item I that maximizes their utility. Now, the nice thing is that if the error has type 1 extreme value distribution as independent across items, then we can write the probability that the user's used choice at time t is equal to I, just in the standard multinomial logit type of functional form. So utility maximization will, where these mu's or the mean utilities, will lead to multinomial logit probabilities. So data about individual I's purchases can then be used to estimate their mean utility. And in particular, if we write their utility, their mean utility, as something that depends on the item and the user, but that's constant over time. So this is just their mean utility for this item, like how much they like a certain transportation choice. And then a second term, which is the product of two terms, the price the user faces at time t for item I, and a preference parameter that's specific to the user. If I have this form of preferences, and then the price varies over time while the user's preference parameters stay constant, I'll be able to estimate how the user feels about prices by looking at how their choices differ across different price scenarios. And if I pool data across users, I'll then be able to understand the distribution of consumer price sensitivities, as well as the distribution of user utilities for different items. So in a paper with Rob Donnelly, David Bly, and Fran Ruiz, we take a look at how we can combine machine learning methods and modern computational methods with the traditional approaches to studying consumer purchase behavior in supermarkets. Now, the traditional approach in economics and marketing is to study one category, like paper towels, at a time. We then model consumer preferences using a small number of latent parameters. For example, we might allow a latent parameter for how consumers care about prices. We might allow a latent parameter for product quality, but other than that, we would typically assume that there's a small number of observable characteristics of items, and there's some common coefficients which express how all consumers feel about those characteristics. The traditional models also assume that items are substitutes within a category, and they would ignore other categories. So you might study consumer purchases for paper towels, ignoring everything else in the supermarket, just throwing all that data away. So what we do in our approach is that we maintain this utility maximization approach, but instead of just studying one category, we study many categories in parallel. We look at more than 100 categories, more than 1,000 products at the same time. We maintain the assumption that categories are independent and that items are substitutes within the categories. And we select categories where that's true. So categories of items where the consumers typically only purchase one brand or one of the item. We then take the approach of a nested logit, which comes from the literature in economics and marketing, where within each category, there's a shock to an individual's need to purchase in the category at all. But then conditional on purchasing, the errors or the idiosyncratic shocks to consumer utility are independent. So having the single shock to purchasing at all is effectively introducing correlation among the probabilities of purchasing each of the items within the category at all. Now, the innovation and where the machine learning comes in is that we're going to use matrix factorization for the user item preference parameters. So instead of having, for each consumer, 1,000 different latent parameters, each one for each product they might consider, instead we use matrix factorization so that there's a lower dimensional vector of latent characteristics for the products, and the consumers have a lower dimensional vector of latent preferences for those characteristics. And that allows us to improve upon, say, estimating 100 different separate category models. We're going to learn about how much you like organic lettuce from whether you chose organic tomatoes. And we'll also just learn about whether you like tomatoes at all from whether you purchased lettuce in the past. So I won't have time to go through it today, but this is just a layout of what we call our nested factorization model, showing the nest where first you decide what to purchase if you're going to purchase, and then the consumer is deciding whether to purchase at all. And we have, in each case, vectors of latent parameters that are describing the consumer's utility for categories and for items. One of the reasons that this type of model hasn't been done in economics and marketing in the past is that what was standard in economics and marketing, if you were going to do a model like this, would be to use either classical methods like maximum likelihood without very many latent parameters, or to consider Markov chain, Monte Carlo, Bayesian estimation, which historically had very limited scalability. What we do in our papers is use variational Bayes, where we approximate the posterior with a parameterized distribution and minimize the KL divergence to the true posterior using stochastic gradient descent. We show that we can overcome a number of challenges. In particular, introducing price and time-varying covariates slows down the computation a fair bit, and the substitutability within categories leads to nonlinearities. Despite that, we're able to overcome these challenges. Once we have estimates of consumer preferences for products, and as well we have estimates of consumer sensitivity to price, we can then try to validate our model and see how well do we actually do in assessing how consumer demand changes when prices change. And so in our data, we see many price changes. We see prices typically change in this particular grocery store that we have data from on Tuesday night. And so in any particular week, there may be a change in price from Tuesday to Wednesday. And so in order to assess how well our model does in predicting the change in demand in response to a change in price, we take held out test data from weeks with price changes. In those weeks, we break the price changes into large price changes and different buckets of the size of the price change. We then look at what is the change from Tuesday to Wednesday in demand in those weeks. Finally, we break out those aggregations according to which type of consumer we have for each item. So in particular, on a week where we have a change in price for a product, we can characterize the consumers as being very price sensitive, medium price sensitive, or not price sensitive for that specific product. And then we can compare how demand changes for each of those three groups. And so this figure here illustrates what we find in the held out test data. And in particular, we find that the consumers that we predict to be the least price sensitive, in fact, don't seem to respond very much when prices change, while the consumers who are most price sensitive or most elastic, as we say in economics, are the ones whose quantity changes the most when prices change. Once we're confident that we have a good model of consumer preferences, we can then try to do counterfactual exercises, such as evaluate what would happen if I introduced coupons and targeted them at individual consumers. We'll take a simple case where we have only two prices we consider, the high price, or the typical price, and the low price, which is the discounted price. Now, what we do is we look into the data and we evaluate what would happen if we sent these targeted coupons out. So for each product, we look at the two most common prices that were charged in the data. We then assess which consumers would be most appropriate for coupons. We might look, for example, and say, I want to give coupons to a third of consumers. I can see which consumers are most price sensitive and most likely to respond to those coupons. I can then actually use held out test data to assess whether my coupon strategy is actually a good one. And that will allow me to validate, again, whether my model has done a good job in distinguishing the more price sensitive consumers from the less price sensitive consumers. So this figure illustrates that for a particular product, there were two prices, the high price and the low price, that were charged over time. In the actual data, the different users might have come to the store sometimes on a low price day and sometimes on the high price day, indicated by blue or red. What we then do is say, well, what would our model say about who should get the high price and who should get the low price? And so we can reassign counterfactually the top 4 users to high prices, indicated by these orange squares, and we can counterfactually reassign the low, the fourth and the fifth and sixth users to the low price, indicated by the green rectangles. Now, since the users we assigned to high saw a mix of low and high prices, I can actually compare how much those users purchased on the high price days and the low price days. And I can also look among the people that I would counterfactually assign to low prices and also see what's the impact of high prices versus low prices for those consumers. And I can use those estimates to assess what would have happened if I reassigned users according to my counterfactual policy. When I do this, I can compare what my model predicts should happen in the test set to what actually happened in the test set. And so what I actually find somewhat surprisingly here is that, in fact, what actually happens in the test set is even more advantageous for the firm than what we model predicts. So in particular, our model predicts that if I reallocate the prices to the consumers according to what our model suggests would be optimal from a profit perspective, we can get an 8% increase in revenue. That is, instead of varying prices from high to low from day to day, we always kept them high, and then we targeted the coupons to the more price sensitive consumers. In the data, if we actually look at what happened in our held out test data, it looks like that the benefits to high versus low prices and the difference in those benefits between the high and the low consumers are such that it looks like in the test set we would have actually gotten more like a 10 or an 11% increase in profits had the prices been set in that way. So to conclude, the approach that I've outlined is to try to learn parameters of consumers' utility through revealed preference. That is, use the choices that consumers make to learn about their preferences about product characteristics and prices, and then predict their responses to alternative situations. It's important to find a data set that's large enough and has sufficient variation in price to isolate the causal effects of prices and also assess the credibility of the estimation strategy. And it's also important to select counterfactuals to study where there's actually enough variation in the data to be able to assess and validate whether your estimates are right. And so I illustrated two cases where I was able to use test set data to validate the approach. You use the training data to assess, for example, which consumers are most price sensitive, and then look at the test data and see if their purchase behavior varies with price in the way that your model predicts. In an ongoing work, I'm trying to understand how the different types of data create value for firms. And so in particular, firms are using the kinds of machine learning models that I've been studying, and they use those estimates in order to do things like target coupons. We can ask, how much do profits go up as they get more data? And in particular, how does that answer vary if it's more data about lots more consumers, or if we do things like retain consumer data for a longer period of time? And preliminary results are showing that retaining user data for a longer period of time so that you really get to know an individual consumer can be especially valuable in this environment. Overall, I think there's a lot of promise in combining tools from machine learning like matrix factorization, but also could be neural nets, with some of the traditional approaches from causal inference. And so here we put the things together. We used functional forms for demand and the concepts of utility maximization and approaches to counterfactual inference from economics and marketing, but used computational techniques from machine learning in order to be able to do this type of analysis at large scale.
Hi guys, good afternoon. I'm glad to be here online today. Thank you for coming. Also, thank you for the organizer. I appreciate the organizer, Amit and Emery, for inviting me to speak in the event today. My name is Elias Barrenbaum. I'm from the computer science department and the Causal Artificial Intelligence Lab at Columbia University. Check my Twitter if you are interested in discussion, sometimes heated, about causal inference, artificial intelligence, and machine learning. Also, apologies for my voice. I'm a little bit sick, but very happy to be here today. I will be talking about what I have been thinking about the foundations of artificial intelligence, how it relates to causal inference, and these notions of explainability and decision making. Let me start from the outline of the talk. I'll start from the beginning, defining what is a causal model. I introduce three basic results that are somewhat intertwined. I usually say that if you understand them, you understand like 50% of what causal inference is about, because there's a lot of more technical results, but the conceptual part that is the most important. The first I will start with structural causal models, which is the most general definition of causal model that we know to date, that is by Pearl himself. Then I'll introduce the second and third, or I would say the second result, which is known as the pro-causal hierarchy, the PCH, which was named after him. This is the main metaphor or object, or mathematical object, used by Yuda Pearl himself, and Dana Mackenzie in the Book of Why. If you haven't read the book, please, I strongly recommend it. It's pretty good since it discusses the foundations of causal inference, how it relates to the future of AI and machine learning. more prominently in the last chapter, as well as the intersection of the other sciences. This is work partially based on the chapter that we wrote in honor of Yuda on prose hierarchy and the foundations of causal inference. This is joint work of Juan Correa, Dulliger, Ibelin, and Thomas Eichert. The first my student at Columbia, and the last two are collaborators from Stanford University. This is kind of the link here to the chapter. Take a look, because most of the things that I'm talking here is there in some shape or form. Then I'll move to another result that is called the causal hierarchy theorem. Which was proven in the chapter, is maybe a 20 plus years old open result, and used as one of the main building blocks, as one of the main metaphors in the book of White. Then I will try to connect with mainstream machine learning, and more specifically with supervised, unsupervised, and reinforcement learning. How does it fit, or how it fits with this PCH of the causal hierarchy, also called the ladder of causation in the book. Then I'll move to talk a little bit about what is causal inference and cross-layer inferences. I will then move to the design of artificial intelligence systems with causal capabilities. I will connect with modern machine learning methods and refer to or try to put deep learning and RL in perspective. And my focus here will go more on my goals to introduce the ideas, principles, and some tasks. I will not focus on implementation details. Also, I should mention that essentially this is the outline of my course. That is a semester course at Columbia. Bear with me. I'll try to give you the idea. If you're interested to learn more, check the reference or talk with me, send me a message. Now, without further ado, let me try to introduce you the idea of what is a causal model or a structural causal model. And we'll use the idea, or leverage this idea from the processes. We'll take a process-based approach to causality. And the idea is borrowed from physics, chemistry, sometimes economics, and other fields that we have a collection of mechanisms that underline some phenomena that we're analyzing. In this case, suppose that we're trying to understand the effect of taking some drug on the headache, and those are observable variables. And we have the corresponding mechanisms here, F sub D for the variable drug, and F sub H to the variable headache. Each mechanism takes as input, or has as argument, a set of observables, in the case of F sub D age, and unobservables, in this case U sub D. This unobservable here is like all variables in the universe that generate variation to drug. That is not age can be included in this U sub D. And the same here with the U sub H. There is the drug and age that are observables, goes to the transformation F sub H with the U sub H. Again, all variables in the universe that are not drug and age, and someone will have or not have headache. This is the real processes. Usually we have a possibly complicated function here in this F sub G, F sub H that is instantiated. Usually we have some type of coarsening, and this is the causal graph related to this collection of mechanisms. The causal graph is nothing than the partial specification of the system, in which the arrows here just means that some variable participates in the mechanism of the other. But I just put X, Y, Z to make our communication easier. Now we have, for example, that age participates in the mechanism of headache, F sub H. Then there is an arrow here from Z to Y, from H to headache. The same with drug. There's this arrow from X to Y, and the same age here also participates in the F sub D. Note here that in the graph, we don't have the particular instantiation of the function. We are just preserving the arguments that we have there. Now, for sure, we can try. This is the process that is kind of unfolding in time. We can sample from a process like that. This gives rise to a distribution, observational or non-experimental distribution over the observables P, Z, X, and Y in this case. Usually when you are doing machine learning, supervised learning, or unsupervised learning, we are playing about this side here of the equation. Here we are trying to understand causality. Causality is about when you go to the system and you change something, or you overwrite some, as a computer science, we like this, we overwrite some function. Here we like to overwrite the equation, the natural way of how people is taking drug. Here is drug is equal to yes. This is called also introduced organically given the time, but this is related to the do operator in which you overwrite the original mechanism f sub d. In this case, is do x is equal to yes. That now we no longer have our original equation. We have a constant here, and you can have another constant that is a constant no on the other side. I don't have time in the slides, and this is that's what we have. This is semantics without necessarily having access to the mechanism themselves. This is the meaning of the operation. Now here is the graphical counterpart of that. Note that there is the f sub d here. We no longer has the age as an argument of this function. There is just the constant. Then you put the constant here, and we cut relative to this graph. You cut these incoming errors throughout the x. This is the mutilated graph. Again, if you are able to contrive reality in this way, you can sample from this distribution or from this process, which gives rise to the distribution called interventional distribution or experimental distribution, P of zy given do x is equal to yes. Now, I use these variables here, x, z, and y, but x could be any decision, y can be any outcome, and z can be any set of covariates or features. Now, what is the challenge here? The challenge that in reality, this upper floor here is almost never observed. This is usually called unobserved. This is why I put in gray. Then this is one of the things. We don't have that in practice or very rarely. And another challenge, usually observe the data that we have is coming from the left side, that is coming from this naturally unfolding or how the system is naturally evolving. And we would like to understand what is the effect if you go there and do the intervention in the system and with our own will or deliberately as a policymaker or decision maker decide to set this variable x is equal to yes. Then we have data from the left from seeing, and you like to do inference about what would happen if you do something in this system. Now, we can try to generalize this idea and define what is the structural causal model. This is chapter in Causality book Pro 2000. I'll not go to the definition step by step. I'd suffice here to say that we have a set of observables or endogenous variables like age, drug, or headache. We have a set of exogenous, or as I said, unobserved variables that could be the u sub d and the u sub h that we have before. And we have a collection of mechanisms for each of these observed variables. We have a mechanism, the f sub d or f sub h, excuse me. This tree here is related, it could be seen as some type of Newtonian physics to kind of summarize the conditions outside the system. Excuse me. Outside the system, if you want to summarize, you kind of sprinkle mass or probability mass, and you have this probability P of u over the exogenous variable. Now, we understand very well how the systems work. There is this awesome work by Halpern, as a logician in Cornell, and Galles and Pro, giving this type of very solid type of understanding over the systems. Now, today we are interested in a different result that is the following. Once we have a SCM, a structural causal model M, that is fixed for the particular environment or setting that we embedded the particular agents, this induces this pro-causal hierarchy or the PCH that is called the ladder of causation in the book of Y. Let's try to understand what is the PCH. Here is the PCH. There are different layers of the hierarchy. This is the first layer that is called the associational layer. It's related to the activity of saying. How would saying some variable x is equal to small x change my belief in the variable y? Or what does a symptom tell us about the disease? Syntactically, this is written as this P of y given x. Quite important, people ask this layer, but this is very related to the machine learning, supervised and unsupervised learning. There are many different types of formulas. There are Bayes nets is one type of model of formulas for there. You have decision trees, you have super vector machines, you have the deep neural networks and other types of networks. They all live in this layer here. Quite important, we have been trying to scale up inferences here, given this x could be the pixels themselves, or a set of features could be in the order of thousands of even millions. And we like to try to predict a y that is some label. You have kind of pixels and you like to know if it's a cat or not. It's kind of classic, and it's very hard we're kind of mastering that or understanding pretty well how to do that in recent breakthroughs in the field, or in the last 20 years, I should say. Now I have a qualitatively different layer, that is layer 2, that is the interventional, is related to the activity of doing. What if I do X actions? What if I take the aspirin? Will my headache be cured? The counterpart in machine learning will be reinforcement learning. You have a causal Bayesian networks, Markov decision processes, partially observable MDPs, and so on. Quite important. I will comment more about that. Symbolically, by the way, you say P of Y given do X, comma C. That's the notation that we have. Now I have a qualitatively different layer, that is layer 3. That is a counterfactual layer. I'll go back here soon, but it's related to the activities of imagination. If you want agents to have imagination, retrospection, introspection, blame, responsibility, credit assignment. It is the layer that gave the name for the book of why. This is the why type of question. What if I had acted differently? Was it the aspirin that stopped my headache? Syntactically, we have this kind of nested counterfactual here. I took the drug, that is X prime, as instantiation of the big X. Pardon for my license here. X prime, I took the drug, and I'm cured, that is Y prime. Now you can ask, I would be with the headache, that is Y, the opposite of Y prime, had I not taken the drug, that is the X, that is the opposite of X prime. I took the drug and I'm good, X prime and Y prime in the actual world, in this world, and I ask, what if I hadn't taken the drug, that is X, would I be okay, that is the Y, or not okay, that is the Y. Okay would be not Y. Then there's no counterpart exactly in machine learning. If you have some particular instance, you can ask me offline, but because whatever, there is all kind of things written in the literature. This comes from the structural causal model. Now I would like to try to see what is going beyond machine learning. I already have just mentioned this layer 3 here. Specifically, I would like to highlight a different family of tasks, of inferential tasks, which follows very naturally causally, that is called this cross-layer tasks, cross-layer type of inferences, as I'm saying here. Layer 1 is related to saying, suppose that as input, we have some kind of data here, and most of the available data today is observational. It's possibly collected. Elias numbers here, 99% of the data that we have is coming from layer 1. And Elias numbers as well, you can blame me if someone complains with you, but 99, or let's put 90% of the inferences that we want to do today is about doing, or action, or layer 3 about counterfactuals, and about policies, treatments, and decisions, just to cite a few examples. Then research question that we're trying to answer here across layers, that we have the data and the inference that we want to do, is how to use the data collected from observations passively, that is layer 1, maybe coming from the hospital, to answer questions about the interventions, that is layer 2. Under what conditions can we do that? Now, why is this task different? Is usually a good question. Why is the causal problem non-trivial? The answer is like SCM are almost never observed, but for a few exceptions, such as in fields such as physics, chemistry and biology sometimes, in which the very target there is to learn about this collection of mechanisms. In general, we do not observe the SCM. In most of the fields that we are in AI machine learning, we are interested that there is the human in the loop, some type of interactions that we cannot, given that we cannot read minds, and we don't kind of isolate the environment in some kind of precise way, you don't have a controlled environment, usually you cannot get the SCM itself. Still, the observation here that the PCH still exists, this collection of mechanisms that underlies the system that we're trying to understand is still there, inducing the PCH, and you could still have the query or the task, the cross-layer task. How can you get from data that is from a fragment that we have from the SCM? You can try to infer about that is layer 1, observational. How can you answer the question in layer 2? Then you have this unobserved phenomena here, and you are trying to get fragments that are observed, some other fragments that are at least realizable. That could be layer 3 as well. How can you move across these layers? I like a lot, I use in the class and we spend a little bit of time, but I like the allegory of the Plato's cave as a metaphor here, since there is this complicated reality. Usually you just observe the fragments or the shadows of these realities, that is kind of fragments of the PCH, and we like to do an inference about the outside world. Under what conditions can you do that? That's kind of the flavor or the consequence of this mechanism that could be the other layers, layer 2 or layer 3, for example. I would like to talk about possibility results or this cross-layer inferences. As usual, let me read the task here. Infer the causal quantity y given to x from layer 3 from observational data that is layer 1. That's exactly the task that I just showed. Now, the effect of x and y is not identifiable ID from the observed data. Proof: there exists a collection of mechanisms or SCMs capable of generating the same observed behavior, layer 1, P of x and y, while disagreeing with respect to the causal query. To witness, we'll show two models. This is model 1, this is model 2, such that they generate the same. I'll not parse the model here. It's just for you to go home and think a little bit, but there are two simple models here. This is XOR, by the way, not X XOR U. There are these two models generate the same observed. This is model 1, P1 and P2, the same observed behavior in layer 1. However, they generate different layer 2 behaviors, different layer 2 predictions. In this case, layer 2 here is saying that the probability of y given to x1 is equal to half, while model 2 is saying that is 1. Then, in other words, we have a kind of layer 1 underdetermines what can we say about layer 2. There's not enough information there to move. And we can, anyhow, that's the result. I would like to now make a broader statement or generalize this idea. Again, this is joint work with Correa, Ibelin, and Icart from the paper that I mentioned earlier. That's prove the following result. Theorem: with respect to Lebesgue measure over, there's some kind of technical conditions, measure over SCM. The subset in which any PCH collapse is measure 0. Let me read the informal version here. You go home later and you can try to parse that. But informally, for almost any SCM, in other words, almost any possible environment in which your agent or your system is embedded, the PCH doesn't collapse. In other words, the layers of the hierarchy remains distinct. In other words, you have this hierarchy here. There is some kind of, this will not happen, that one layer usually underdetermines the others. There is more knowledge in layer 2 than in layer 1 alone. There is more knowledge in layer 3 than in layer 1 and layer 2. Then one layer underdetermines the other. You don't get this type of situation. This closes the open problem. I say that is stated in the book of Y. As a corollary, you can go to chapter 1 that says that to answer a question at layer I about a certain type of interaction, could be layer 2 about the intervention, one needs knowledge at layer I, 2, or above. Now, the natural question here that we could be asking is like, Elias, then after all, how are causal inferences possible? Or how are causal inferences possible? I get commonly now, is this impossible? Does it mean that we shouldn't do causal inference at all, given that we have this type of underdetermination from one layer to another? And the answer is not at all. The idea here, this motivates the following observation. If you know a little bit about, if you know 0 about the SCM, this is the CHT, the causal hierarchy theorem that I just gave. If you know a little bit about the SCM, maybe possible. And what is this little bit? Little bit is what we call the structural constraints, which can be encoded in a graphical model. You have different graphical models here. You can have a graphical model that is a layer 1 graphical model, layer 2, and so on. Then in principle, it could be possible to move across layers, depending on how you encode these constraints here. There's new families of graphical models. I would like to examine it just for 1 minute, the graphical model layer 1 here that is very popular, such as a Bayesian network that is layer 1 versus a causal-based net. But I will start with a Bayes net. These not all graphical models are created equal. This is the same task. From the previous theorem, it was shown that it's impossible to move from layer 1 data to layer 2 type of statement. Now, what if you have a Bayes net that is compatible with the data? Now, this is a Bayes net that is compatible with the data, x pointing to y, whatever data we get over xy, and we would like to know what is the P of y layer 2 quantity, y do x in this case. If you play a little bit, or if you know a little bit of causality, there is no unobserved confounder here in this graph. Then the P of y given to x is equal to P of y given x. By ignorability or backdoor admissibility, those are names that you use to say this unobserved confounder. Now I'd like to pick another BN, another layer 1 object, flip the arrow, no longer from x to y, but is from y to x, and see what would be the causal effect of x and y. In this case, the y given to x, still compatible. Now it turns out for the semantics of causal inference or of intervention, the do, you'll be cutting the arrow here that is coming from the x, because we are the one controlling the system, which give P of y given to x turns out to be equal to P of y. Then this here highlights that they have different answers. We couldn't. There is not enough information about the underlying SCM in the BN, so as to allow causal inferences. Just say that this is not good, even though the constraints could be coming from the SCM, still a layer 1 object is not good. This is not a BN that we're looking. Now I'd like to consider a second object that is a layer 2 kind of graphical model. You go to the paper that we define more formally. I'll not do that here, but it's possible to encode layer 2 constraints that are coming from the SCM, the idea of the asymmetry of the causal relations, and we like to focus on this one now. Now, the idea is like there are positive instances that we can do cross-layer inferences. Let's consider a graphical model that is a L2 graphical models. The mental picture that I would like you to construct is the following. Suppose that this is the space of all structural models. Here are the models compatible with the graph G. That is a L2 graphical model. These are the models that SCMs compatible with PV could generate this observed distribution. And here are the models that are the intersection of these guys. You have the models that are giving the same y given to x. What I'm saying in reality, there are situations that for any 2 structural model encoding this unobserved nature, let's call nature n1 and 2, such that they have the same graph G of n1 is equal to G n2 layer 2. If they generate the same PV, the same observed distribution, then they will generate the same causal distribution. Then that's the notion of identifiability. It is possible to get in some settings. Then let me try to summarize what I said so far. It's about some sort of tension between the reality that is this true underlying mechanism that we don't have, and our model of reality that will be the graphical model, for example, could be other, and the data. We started from a well-defined world, semantically speaking, in which an SCM, a pair F and P of U, mechanisms and distribution over the exogenous, implying the PCH, these three, which means these different aspects of underlying nature and types of behavior, layer 1, layer 2, layer 3. We do acknowledge that the collection of mechanisms are there, but inferences are limited given that the SCM is almost never observable or observed. Due to the CHT, we have this constraint about how to move across the layers. Now we move towards scenarios in which partial knowledge of the SCM is available, that is encoded such as a causal graph, a layer 2 causal graph. Causal inference theory then help us to determine whether the targeted inference is allowed. In the prior example, the inference is from layer 1 to layer 2. Namely, we are trying to understand if the graph plus the PV that is layer 1 distribution allows us to answer the P of y given to x. Now, observation here, sometimes this is not possible. I mean, for weak models, if you have a weak model, the mental picture here is like sometimes the true model is generating this green guy here, this distribution. There is another model that have the same graph G. It can induce the same observation distribution and generate another guy that's called P star of y given to x. Then you're in a situation that we cannot do the inference about layer 3 just with L1 data. Now I would like to spend 2 minutes just doing a summary of the how does reinforcement learning fit into this picture. I spent almost 3 hours in a tutorial last week in ICML talking about that. Go to the crl.causalai.net if you want the details. I'll try to give in 2 minutes what happened there. This is the PCH. Now my comment here that typical RL is usually confined to layer 2 or subset of layer 2. Usually we cannot move from layer 1, we cannot leverage the data that is from layer 1, or very rarely. And this also RL doesn't support us to make statement about layer 3 or about counterfactuals, layer 3 type of counterfactuals. Then that's the global picture. This is the kind of canonical picture of RL, that we have an agent that is embedded in the environment. The agent is a collection of parameters. The agent observes some kind of context of states, commits to an action, and then observe a reward. There's a lot of discussion about being model-based or model-free. I would like to say that all model-based that they mentioned today in the literature is not causal model-based, it's acausal. It's important to not get confused. You can ask me more later. Now, the only difference here from the causal reinforcement learning perspective, that is what that we leverage, and I spent almost 3 hours discussing that in the tutorial, that now officially the collection of mechanisms that we just studied, the structural causal model, will be the model of the environment officially, and the agent side will have this graph G. Now the two key observations, again, the environment and the agent will be tied through the pair SCM in the environmental side, and the causal graph in the agent side. We'll define different types of actions or interactions following the PCH, which means that observing, experimenting, and imagining will be these different modes. Please check the crl.causal.ai for more details there. Let me skip this one here. You can check later about the different types of tasks that were not acknowledged before. I would like just now to move quickly and spend 30 seconds discussing how does the deep learning fit in this picture. Here's the same picture that I had before from the left side, observational, in the 10 slides ago, and the right side, the interventional world. Now I would like to, in reality, this is about reality and model. This is every abstraction. In reality, we have a data, and you can sample from the data, and this allows us to get the hat distribution, the p hat, and we have some results saying that the distance between the hat distribution and the original distribution keeps decreasing, which makes sense to operate in terms of the hat distribution. Now, for sure, you can use some kind of formalism to try to learn the hat distribution, including a deep network or a variation of that. Now, challenge, usually you are interested in this inference in the right side, and you have 0 data points in the right side. I'm talking broadly, not reinforcement learning. The reinforcement learning have other problems, but you have 0 here. Now, how on earth can you learn about the hat of this distribution? Some people is connecting the output of the DNN that you learn from the left side to the right side, which is kind of, I put a guy like that. There is nothing in the data, in this data, nor in the deep net, that takes into account the structural constraints that you discuss, and nor the CHT. Then it makes no sense to connect. There's something missing there. Then I could talk maybe 1 hour. You invite me to talk about the relationship between neural nets and causal inference, but I think this is the picture that I want to start the conversation. Now, I would like to conclude, and apologies for the short time. It's like very, very short talk, but and thanks for the opportunity. Now, let me conclude. Causal inference and AI are fundamentally intertwined, and novel learning opportunities emerge when this connection is fully understood. Most of the impediments for general AI today are orthogonal to the current acausal methods available in ML. We're not even touching the problems, the impediments for general AI, including deep learning, the huge advances that we have in deep learning and reinforcement learning. In practice, failure to acknowledge the distinct features of causality almost always lead to poor decision-making and superficial type of explanations. The goal here, the agenda that we have been pursuing maybe for almost 10 years now, we like to develop, we are developing a framework, a set of principal algorithms and tools for designing causally sensible AI systems integrating these 3, PCH, observational, interventional, and counterfactual data, modes of reasoning, and knowledge. And my belief strongly is that this will lead to a natural treatment of human-like explainability, given that we are causal machines, and rational decision-making. I would like to thank you for listening, and also this is joint my collaborators. This is joint work with the Causal AI Lab at Columbia, and collaborators. Thank you, Juan, Sangak, Janzi, Yuda, Andrew, Dulliger, and Thomas, and all the others that are. This is a huge effort. Thanks, and I'll be glad to take questions.
Hello, everyone. I'm Cheng from Microsoft Research Cambridge, UK. So today I'm going to talk about a causal view on robustness of neural networks. So deep learning has been very successful in many applications. However, it's also vulnerable. So let's take our favorite MNIST classification, for example. So deep learning can achieve it with 99% accuracy. This is impressive. However, if we just shift image a little bit, not much, the safe range won't be more than 10%. So the accuracy will drop to around 85%, which is already not satisfying for an application. And if we enlarge the shifting range to 20%, the accuracy will drop to half, which is not acceptable anymore. The plot shows that the more we shift, the more the less the performance. This is not desired, especially with minor shifts. Okay, now we would like to be robust. Let's add vertical shifted image in the training set as well. This is adversary training setting. I have added the image that shifts up to 50% of the image in the training set, so that you can see that the performance is much better with about 95% accuracy, even when we shift up to 50%. But do we solve the problem now? What if I didn't know that it would be vertical shift in the test and thought it would have been horizontal shift? Then I'll add horizontal shift in the training data. Then during the testing time, we test the image with vertical shift as before. The orange line shows the performance with vertical shift. It is actually even worse than training with clean data only. So adversary training does not solve the robustness problem in deep learning because it can even harm the robustness to unseen manipulated images. And we will never know our possible attacks. This is a real issue of deep learning. This is a simple task with handwritten digits. How about healthcare or policy making? The decision quality is critical. But humans are very good at this task. We can recognize the digit if it is shifted a little bit, or if the background changes. Because we're very good at causal reasoning, we know that shift or background changes does not change the digit number or make a cat to a dog. This is a modular property of causal reasoning, and it is also referred as independent mechanism sometimes. So the causal relationship from the previous example can be summarized in this way. The final observation is an effect of three types of causes. One is the digit number, and the other one is the writing style, etc. And the last one is different manipulations, such as shift or rotation. The same applies to the animal example, where the observation of cat is an effect of a real cat, and its fur color, etc. features, and different environments, such as different view angles or backgrounds. We use Y here to denote the target of the task, and Z denotes the factors that cannot be manipulated, and M denotes the factors that can be manipulated manually. So M here is a factor that we would like to be robust to. Before diving down into the robustness details, let's review what is a valid attack. We have seen the shifts of MNIST digit or background change of the cat. Another common way is to add a little bit noise, as we see here. With just a very small amount of noise, we can fool a deep learning model to classify the panda as a gibbon. We can also rotate the image and even add stickers sometimes. But it has also been pointed out that adding some small noise can also fool human. In this case, the left image looks more like a dog than a cat to me. The question now is this still a valid attack? What type of change and how much change can we consider that can still form a valid attack? We would like to define a valid attack from a causal lens. Let's take the previous example. From a causal view, we can consider valid attack are generated from an intervention on M. Together with original Y and Z, it produces manipulated data X. In general, a valid attack should not change the underlying Y because this is the target. Thus, we cannot intervene the target y or parents of y if there is any parents of the y. While z are not able to intervene by our definition, such as the genetic feature of a cat or writing style of the image itself. In this regard, recent adversarial attacks can be considered as specific types of intervention on M, such as the adding noise or manipulating the image. In this way, a learned predictor is deceived. So the goal of robustness of deep learning is to be robust to both the known manipulation and the unknown manipulation. Adversarial training can help with the known manipulation, but it fails at unknown manipulation. So our question is how to perform a prediction that can be adaptive to the potential unknown manipulations, as the shifted digit example. In this work, we propose a model naming Deep Causal Manipulation Augmented Model. We call Deep Karma. The idea is to create the deep learning model that is consistent with the underlying causal process. In this work, we assume that the causal relationship among the variables of interest are provided. The deep karma is one of the generative model. Let's quickly recall the deep generative model variational autoencoder. Variational autoencoder bridges deep learning and probabilistic modeling, and it has been very successful in many applications. The graphic model is shown on the left. From a probabilistic modeling point of view, we can write down the model as this, which is factorized in the way shown in the right-hand side of this equation. We learn the posterior of Z using variational inference. In particular, we can introduce a variational distribution Q, and we can try to minimize the divergence between the P and the Q. We can follow the standard step and form the evidence lower bound. We call it elbow, and optimize this evidence lower bound to get the posterior estimation. Different from traditional probabilistic modeling, every link in the graphic model on the left are all deep neural networks. This becomes an autoencoder where we can try to reconstruct the X with a stochastic code Z. This can be learned as a standard deep learning framework with the loss using the evidence lower bound we just showed before. So Karma is also a deep generative model. Instead of simple factorized like the BAE on the left, our model is factorized in a causal consistent way. You can see it in the right-hand side. The model is consistent with the causal relationship that we saw before. Next, let's see how can we do the inference. When we only have the clean data set, which means like the data set without any augmentation or any adversary examples. So in this way, from a causal lens, this is the same as do M equals clean. Now we translate it to the deep karma model. We can use value 0 indicating the clean data. Thus we set M to be 0, and we can consider it to be observed. We only need to infer the latent variable Z in this case. For variational distribution, instead of conditioning only on X as traditional in variational autoencoder, in Karma we can use X, Y, and M together to define the variational distribution. We follow the same procedure and form the evidence lower bound, elbow shown below. As M is a root node, we have do M, and the do calculation can be rewritten as conditioning. And in the adversarial training way, we may have manipulated data in the training set as well. In this way, we may not know the manipulation. We just treat M as a latent variable. In this case, we need to infer both M and Z. Thus, we have the Q phi ZM condition on X and Y. Again, we can write the evidence lower bound in this form. Finally, with both clean and manipulated data in the training set, the final loss is in a combined form with corresponding loss for the clean data and manipulated data as shown before. Here, D is a clean subset of the training data, and D prime is a subset of the data which are manipulated. This is the adversary training setting using Karma. In this way, Karma can be used either with only clean data and with manipulated data together. The final neural network architecture are shown here. So the encoder and decoder are shown on the right. The decoder network corresponds to the solid error in the graphic model in the left side. And then the encoder network corresponds to the dashed lines. So the inference network can help us to compute the posterior distribution of M and Z. In the test time, we would like the model to be robust to unseen manipulation. With this, we would like to learn M in the test time, while with the network representing the generative process from Y and Z to X fixed. Thus, we fine-tune the network to adapt to the new M and how M influences X, so that in this way, the network can learn a new unseen manipulation. At test time, the label is not known, so we don't know the Y. In this way, we need to marginalize Y and optimize the fine-tuning loss here to adapt to the unseen manipulation. For prediction, we use the Bayes rule to infer the posterior of the Y with impotence sampling. As we can see, Karma is designed in the causal consistent way. We can efficiently train the model following similar procedure as variational autoencoder. We can also fine-tune the model in the test time to adapt to unseen manipulation and make prediction. Next, let's see the performance of Karma. First, let's use only the clean data, as we see in the first slide of this talk. We bring the blue curve from the first slide, which is a regular deep neural network. Our model without fine-tuning is shown in orange. With fine-tuning on the corresponding manipulation in the test time, which is shown in the green curve in the figure A, we can see significant improvement in the performance in the figure A. We can also see with fine-tuning on a different manipulation in the middle panel, the performance does not drop, unlike the traditional neural network. This is thanks to that we fix the mechanism from Y and Z to X. So fine-tuning on one type of manipulation does not affect the robustness to other type of manipulation, which is desired. So in the middle panel, the fine-tuning was done on the horizontal shift and the testing was on vertical. Furthermore, we use different percentage of test set for fine-tuning. We see that the more data we have for fine-tuning, the more robust we have for the performance for the unseen manipulation. More importantly, we can see that with only more than 10% of the data, we already obtain very good performance, which means that the fine-tuning procedure is very data efficient. We also tested our method with popular gradient-based adversary attacks, in particular the fast gradient sign method as shown on the left and the projected gradient descent attack method as shown on the right. The blue one is a traditional deep learning method, which is very vulnerable. The orange one is a Karma model without fine-tuning, and the green one is the one with fine-tuning. We can see that Karma with fine-tuning is so much more robust to even gradient-based attacks. The red line shows the clean test performance after fine-tuning, which shows that the fine-tuning does not deteriorate the clean data performance either. So the improvement in the robustness of Karma model compared to the traditional model is significant with gradient-based attacks. With adversary training setting, we can obtain similar results as with clean data we see before. Please see our paper for more results. I will not repeat here. But moreover, I would like to say that our method can obtain natural disentanglement due to we model Z and M separately. And we can even apply do operation to generate counterfactual examples. Figure A shows some examples that are vertically shifted in the training data. After fitting the data, we can apply do M operation and set do M equals 0 and generate new data, which is shown on the right-hand side. You can see that we can shift the image back to the centered location. Now we have shown that Karma works well in the image classification case. And how does it work for general case? For example, with many variables and much more complicated causal relationships, such as the one shown in the picture. For example, with the rain, there can be multiple causes, and whether the road is wet or not can also be caused by multiple factors. For example, both whether it is raining or not, or the hydrant is broken or not. Can we use karma in this case? The answer is yes. We can have generalized deep karma in this setting. We consider the macro blanket variable of interest, and we can build a deep generative model that is consistent with the causal relationship. With target Y, we put other variables in the corresponding location, which are either ancestor A, children X, and co-parent C, that is consistent with the causal relationship. We introduce Z and M in the same way, where Z represents the hidden factors, which cannot be intervened, and M is the hidden manipulations. We also extend the inference and fine-tuning methods in the same way for this generalized deep karma model. We will use synthetic data which have complicated causal relationship for the experiment. We shift the children the data set for testing. Again, blue line is the baseline, and the orange line is the one without fine-tuning, and the green one is the one with fine-tuning. We can see that such generalized deep karma is significantly more robust, and the red line shows the test performance on the clean data after manipulation, and we see that the clean data performance remains high even after the model has adapted to on-scene manipulation. The same holds for gradient-based adversarial attacks. The attack can be on both children and co-parents, which are valid attacks as the target Y remains the same. Comparing the green line and orange line to the baseline, which is in blue, our method is significantly more robust to gradient-based attacks. Last, you may ask, what if we don't have causal relationship? As till now, we always assume that the causal relationship is given already. In general, there are many methods for causal discovery from observational data and interventional data. So given a data set, you can use different tools to find the causal relationship. A good review paper is provided by Clark etc. last year, which summarized different types of causal discovery methods. Myself also did some research on this topic. However, just to be honest, the causal discovery is a challenging problem, and the result may not be perfect all the time. So what if the causal relationship that we use was not completely correct? There may be small errors. So here we performed experiments to show it with the synthetic data with many variables. The blue line is the baseline, and the orange line is the case when the causal relationship is perfect. So here, different color of lines shows different degree of mystification in the causal relationship. In this experiment, we have 10 children variable in total, and we make them have different degree of misspecified causal relationship. The green line shows that 2 variables are misspecified in the causal relationship, and the red line means 4 variables are misspecified. We see that with misspecified causal relationship, the performance drops comparing to the ideal scenario. However, if just misspecify a small fraction, we can still obtain more robust results comparing to the baseline. Thus, it is helpful to consider causal consistent design, even we may not have the perfect causal relationship given. In the end, I would like to summarize my talk. I present the causal view on model robustness and the causal-inspired deep generative model called the deep karma. Our model is manipulation-aware and robustness to unseen manipulation. This is efficient with or without manipulated data during training. Please contact me if you have any questions. Thank you very much.
Right, so we are back live for the panel session. I think one of the questions that was asked a lot during the chat was this question about model misspecification. And model misspecification can happen in 2 ways. One is that while we are thinking about the causal assumptions, we may miss something. So there could be, for example, an unobserved confounder. And the other way could be that when we build our statistical model, we might parameterize it too simply or too complex, and so on. So maybe this is a question for both Susan and Elias, is how do you reconcile with that? Are there tools that we can use to detect which kind of error is happening? Or can we somehow give some kind of confidence intervals or guarantees on when we are worried that such errors may occur? So maybe Susan, you can go first.
Sure, that's a great question, and it's definitely something that I worry about a lot about in different aspects of my work. So I think one approach is to exploit additional variation. So I guess we should just start from the fact that, in general, in many of these places, these models are just identified. So there's a theorem that says that you can't detect the presence of the confounder without additional information. But sometimes we do have additional information. So if you have multiple experiments, for example, that you can exploit that additional information. And so in one of my papers, we do an exercise where we try to assess, we can look at certain types of violations of our assumptions and see if we can accept or reject their presence. So, for example, one thing that we worried about was there might be an upward trend over time in demand for a product that might coincide with an upward trend in prices. So we were already using things like weak effects and throwing out products that had a lot of seasonality, but still our functional form might not capture everything. And so we did these exercises called placebo tests, where you put in fake price series that are shifted up or shifted back, and then try to assess whether we actually find a treatment effect for that fake price series. And then we had 100 different product categories, so we could test across those 100 categories, and we found basically a uniform distribution of test statistics for the effect of a fake price series, which sort of helped us convince ourselves that at least these kind of overall time trends were not a problem. But that was designed to look at a very specific type of misspecification, and in another setting, there might not be an exact analog of that. Another thing that I emphasized in my talk was trying to validate the model using test data, which again was only possible because we had lots of price changes in our data. And so those types of validation exercises can also kind of let you know whether you're on the right track, because if you've misestimated price sensitivities, then your predictions about differences in behavior between high and low price sensitivity people in the test set won't be right. But broadly, this issue of identification, the fundamental assumptions for identification and testing them is challenging. One of the most common mistakes I see from people from the machine learning community is sort of thinking that, oh, well, I can just test it this way or just test it that way, without realizing actually in many cases there's a theorem that says that even infinite data would not allow you to distinguish things. So you have to start with the humbleness that there are theorems that say that you can't answer some of these questions directly. You need assumptions, but sometimes you can be clever and at least provide some data that supports your assumptions. So maybe I can come back to the functional forms and let Elias take a crack at the first question, and then because there's sort of a completely separate answer for the functional forms, I think. Go ahead.
Sure.
Oops, you're muted. There we go.
Oh, can you hear me?
Yes.
Okay, cool. Thanks, Susan. Thanks, Amit. Yeah, the model misspecification machine learning. First comment that I would say that is very common is people trying to use this idea of the training and testing sets or paradigm, as I usually like to call, to use whatever, to try to validate a causal model or try to validate a causal query or to verify. It makes no sense in causality. As I just kind of summarize in my talk, usually one type of data that we have in the kind of training and testing data is layer one, that is observational data, and we are trying to make a statement about another distribution that is the experimental one. Then there is no training or testing in the world that one distribution can tell you about the other, at least not naively or not in general. And this is the first comment. The second one, I think the interesting scenario, as I mentioned in the chat earlier, is about when you are in the reinforcement learning, before reinforcement learning, in the observational setting. For sure, you can try to get the testable implications of your causal model, condition independence, inequality constraints, and there are many other types of constraints to try to validate the model. I think this will be the principal approach you call testable implications. And a lot of the people doing causal inference is usually trying to understand what are these kind of constraints that we usually have, and then you can submit that to some type of statistical test. Now moving to the reinforcement learning, that is kind of more active setting that I think is quite interesting. In this setting, we already taking the decision. We already kind of randomize on controlling in the environment. Then the very goal of doing that by Fisher, perhaps 100 years ago, was to avoid the unobserved confounding. That was what originated the question. Then reinforcement learning is good for that, and then this is and if you have something wrong, many times I can be super critical about that, but many times the effects that what we have wrong will kind of wash away. I think that's another nice idea in the reinforcement learning setting that we are kind of pursuing, but I think is quite nice and other people should think about, is how can you use the combination of these different data sets, not only to the decision making itself, but try to validate the model, which parts of the model are wrong. And there's kind of different types of tests that are usually very unconventional about how to triangulate these different observational and the different types of experimental distributions in order to detect the parts of the model that have problems. My last note here, my last idea is like just do sensitivity analysis. Usually you don't have so many methods. You have good ones or initial ones, but you don't have so many in particular tailored to the causal inference problem. I think it is a very good area. We have some initial work, but I think it's very promising. And we are talking about the future of frontiers of ML. I think some more people should do sensitivity. I pass the ball here to Amit.
Sure. Yeah, right. I think it's sort of the fundamental distinction between identification and estimation, right? And I think maybe Susan, now maybe you can talk about the statistical misspecification as well.
Yeah, the functional forms, right? I mean, so in econometrics, we often look at non-parametric identification, and look at things like semi-parametric estimation. So you might think, for example, in this choice problems I was talking about, we had behavioral assumptions that consumers were maximizing utility. We had identification assumptions, which basically say that whether the consumer arrived at the store just before or just after the price change was as good as random. And so the price was, within a period of 2 days, was randomly assigned to the consumer. So that's kind of the identification assumption. And then there's a functional form assumption, which is the type 1 extreme value, which allows you to use this multinomial logit formulation. That functional form assumption is incredibly convenient because it tells you that, say, if one product goes out of stock, I can predict how you're going to redistribute your purchases across substitute products. And so it's going to allow you to make these counterfactual predictions, and it's very efficient. And if I change if I have one price sensitivity, it's going to tell me, I can learn that on one product and I can apply it to other products as well. So those types of things are incredibly efficient, and they've been shown to be incredibly useful for studying consumer choice behavior over many decades. But there are still functional form assumptions. And so there are also theorems that say, actually, in principle, you could identify choice behavior even if you don't assume the type 1 extreme value, don't assume this logit formulation. But then you need a lot of variation in prices, like in order to trace out what the distribution of your errors really are, and to fully uncover the joint distribution of all of the shocks to your preferences. You would need lots of price variation in lots of products over a long period of time. So theoretically, you can learn everything without the functional form assumptions, but in practice, it's not practical. And so you're always going to be relying on some functional form assumptions in practice, even though theoretically you can identify everything non-parametrically with enough price variation. So then it comes to sensitivity analysis. You want to check whether your results are sensitive to these to the various assumptions that you've made, and that becomes more of a standard exercise. But I think it's really helpful to frame the exercise by first saying, is it even possible to answer this question, and what would you need? And many problems are impossible. And just as Elias was saying, like, if you have a confounder in your training set, you're also going to have a confounder in your test set, and just splitting test and train, doesn't solve anything. So you have to have a theoretical reason why you think that you're going to be able to answer your question.
Makes sense. In fact, I have a similar question for Cheng as well, in the sense that it'll be great if we have a training method that is robust to all adversarial attacks. But obviously, that will be difficult, right? So there are some assumptions you're making in the structure of your causal model itself in the deep gamma method. So my question to you is, of course, how sensitive it is and what kinds of attacks would your model be robust to? But I'll also throw a more ambitious question, like, is it possible to formally define the class of attacks on which a causal model may be robust to?
So I think the key here is how can we formulate attack in a causal way. So I think for some attack, it's very easy to formulate in a causal way. For example, this shifting, it is a manipulation. It's just another cause for the effect you're observing. But for some attack, it is a little bit more tricky to formulate it in a causal way. For example, the gradient-based white box attack, right? So it is in a causal setting, and especially with this multiple-step gradient-based attack. So I think then it goes to over time with cycle causal model as the underlying model. So I think if you can formulate it properly as a causal model and design a model that is consistent, and then we can be robust to the attack. But not all cases are so easy, or it can be technical challenges when there's cycles over time for certain type of attacks. So I think in general, it's just always good to consider more causality, but how difficult and how much assumption you need to make and in which degree you violate your assumptions, I think that depends on the situation you are in.
Yeah, that makes sense. And maybe I think one question I want to ask, and maybe this will be the last question live, is, so we talked about really interesting applications of causality. So Susan, you talked about sort of the classic problem of price sensitivity in economics. Elias, you briefly talked about reinforcement learning. And Cheng, you talked about adversarial attacks, right? So these are all interesting ideas that we are seeing. I wanted to ask you to look in the future a bit, maybe a few years. What are the areas or applications where you're more excited about, or you think that this amalgamation of causality and machine learning is poised to help or may have the biggest impact? Maybe Susan, you want to go?
Sure, that's a good question. So one thing that I'm working on a lot in my lab at Stanford is just personalization of digitally provided services, education and training, which of course, like all of the partners I'm working with have had huge uptake in the COVID-19 crisis. And so, of course, you can start to attack personalization in digital services without thinking about causality. You can build sort of classic recommendation systems without really using a causal framework. But as you start to get deeper into this, you realize that you actually can do a fair bit better in some cases by using a causal framework. And so, first of all, it's using reinforcement learning, for example, I would argue that reinforcement learning is just intrinsically causal. I mean, you're running experiments basically, but if you're trying to do reinforcement learning in a small data setting, you do want to use ideas from causal inference and also be very careful about how you're interpreting your data and how you're extrapolating. So I think that at this sort of intersection of causal inference and reinforcement learning in smaller data environments where the statistics are more important, worrying about biases that come up when a naive reinforcement learning, you're creating selection biases and confounding in your own data. And if the statistician inside the reinforcement model isn't actually factoring everything in, you can make mistakes. And more broadly, we're seeing, a lot of the companies that I'm working with, the ed tech and training tech, are running a lot of randomized experiments. And so we're combining historical observational data with their experiments. And so you can learn some parts of the model using the historical observational data and use that to make the experimentation as well as the analysis of the experimentation more efficient. And so I think this whole intersection of combining observational experimental data when you're short on statistical power is another super interesting area that a lot of companies will be thinking about as they try to improve their digital services.
Elias, what do you think?
Yeah, Emily, thanks for the question, by the way. I was trying to answer you. Thanks, Amit. I think that in terms of applications, my general goal of the goal in the lab is to build more general types of AI, I would say, that is kind of human, as people say, human friendly. Everyone is using this name, or you have some type of rational decision. You can attach this label rational decision making. I would like to review these notions. I have been doing that for the last maybe 5 years or so. Review what this could mean, because since if you go to books, AI books from 20 or 30 years ago, all of them are using the same label, and they are usually not causal. Then I would say I personally don't see, and I see any way of doing general AI or more general types of AI, I should say, without being serious or kind of attacking causal inference front and center. And I can count in my hands today how many people are doing it. And I cannot count the number of people that's excited, which is pretty good. I'm excited about the level of excitement at the moment. Then my suggestion is like, just don't go around it. Just trying to understand what is a causal model, what causality is about, and then just do it, right? There is a little bit of a learning curve, but I think this is the critical path if you want to do AI or more general types of AIs. The two obvious applications that also we have been working, and just go to our website, causalai.net. But causal reinforcement learning, as you mentioned, we are chatting before in the internal chat here. I just gave almost 3 hours tutorial in ICML that is trying to explain my vision or how I see this intersection of causality and reinforcement learning. Then check it out, CRL, causal reinforcement learning, and all the notions of explainability and fairness and ethics. Again, there are many papers and works that are not tackling causality or saying that causality is hard or it's difficult to get a causal model and so on. It's inevitable in some way. Then there is no point in postponing. If you go to the court or if you talk with human beings, usually causality is required in the law or in legal circles. And in humans, we are causal machines. Then there is no way of going around. Then I would just like to see more people working on it, including Microsoft for sure. Microsoft was the leader, by the way, in the Bayes-Nacht in the early 90s, revolution that takes the 90s until early 2000s, I think, which pushed a lot the limit and led to many of the events that we have today, including variation autoencoders and so on. Still, I'd like to see much bolder steps from Microsoft. I expect it was due to Eric Horvitz and David Hackerman. Those are the two leaders that they understood very well. They are the developers of the theory, even of graphical models of Bayes-Nacht in the late 80s, and they pushed that in such a good way. Now I'm not advertising from the Bayes-Nacht, that's completely different than the causal graphical models. Then this is expectation from Microsoft from my side, and I think huge potential. But anyhow, that's the idea.
Thank you, Elias.
Sure.
And Cheng, what sort of domains or applications you're most excited about?
I would like to second Suzanne and Elias. I think these are all interesting directions. I see like great importance in considering causality in all current machine learning, all other directions, because I mean for deep learning, reinforcement learning, like fairness, I think I really like your work, Amit, as well on the privacy, robustness, generalization. Nice. A lot of current problem in machine learning is like if we actually consider causality, I really see that's the last magic ingredient to solve a lot of these drawbacks in the current machine learning model. But I would like to bring another angle is like if you think about causality and the other direction of machine learning, I think in past years, I mean in recent years, a lot of gap has been bridged, but I think in early days is what I see it's a little bit more separated. So I would like to second that, like from a causal chair, I think a lot of more modern machine learning technique can also improve just the causal discovery itself, because traditionally we care about like all these theorems, proof, and identifiability, and all these things, and commonly we limit ourselves to a simpler functional form. I think in recent years there's a little bit more advances like non-parametric form and other things, but I also do see a lot of advances in the modern machine learning techniques help with causal discovery, for example, with a lot of nonlinear ICA work from Apple recently. It actually bridges nonlinear ICA and VAE, and a little bit of self-supervised learning time series can also help with causal discovery from observational data. And I also see this is a great trend. I mean, like, for example, even from Bernard, some recent work, like how you use like active learning, element-based active learning for causal discovery. So I actually see not only causality as a machine learning, but also see a great potential for other machine learning method to causality itself.
Great. On that note, that's a wrap. Thank you again, all the speakers, for taking your time and attending this session. And of course, thank you all to the audience for coming to the Frontiers in ML event. We'll start again tomorrow at 9 a.m. Pacific, and we'll have a session on machine learning reliability and robustness. Thank you all.
Thank you. Thanks.
See you.
See you, Amit. Thank you.
Yep. See you.